The average lifespan of a car in 1960 was over 20 years. Today, most vehicles barely make it past 12. But this isn't about nostalgia. It's about engineering reality. Modern vehicles come packed with sensors, computers, and intricate systems that could cost you thousands in repairs. Meanwhile, classic cars from the 60s and 70s are still running strong with basic maintenance. Take the 1965 Ford Mustang. Pop the hood and you'll see an engine bay you can actually work on. No plastic covers, no specialized computer systems, just mechanical components built to last. Compare that to a 2024 model, you'll need specialized diagnostic tools just to check why your check engine light came on. Let's break down 3 key factors that made older cars more reliable and longer lasting. First, mechanical simplicity. Older engines operated on straightforward principles. A carburetor delivered fuel and air mixture to the engine, no direct injection computers or variable valve timing to fail. When something went wrong, you could diagnose it by sound and sight. The parts were built oversized and over-engineered, allowing for wear and tear without immediate failure. A perfect example is the distributor system in classic vehicles. Each spark plug received its electrical charge through a single mechanical component that rotated in time with the engine. Modern vehicles use individual coil packs for each cylinder, controlled by complex electronic modules. While this new system might provide better timing, when one component fails, you're often looking at replacing the entire ignition system rather than a simple distributor cap. The fuel delivery system tells a similar story. Carburetors were purely mechanical devices that could be rebuilt multiple times. A skilled mechanic could tune them by ear and with basic tools. Modern fuel injection systems rely on multiple sensors, high-pressure fuel pumps, and computer-controlled injectors. When these components fail, they require complete replacement, often costing thousands of dollars. But here's what car manufacturers don't want you to know about modern engineering practices. Modern vehicles prioritize fuel efficiency and emissions control over longevity. While these goals are important, they've led to components designed to operate within razor-thin tolerances. When these precision parts wear down even slightly, they require complete replacement rather than simple adjustment. Consider the cooling system in a 1968 Dodge Charger. The thermostat, water pump, and radiator work together in a straightforward manner. If the temperature rose, you could diagnose the issue by checking each component individually. Today's cooling systems integrate with multiple electronic sensors, computerized fan controls, and variable speed water pumps. A single faulty sensor can trigger a cascade of problems, leading to expensive diagnostic procedures and repairs. The transmission systems in older vehicles were masterpieces of mechanical engineering. Take the turbo-hydromatic 400 transmission found in many GM vehicles of the 60s and 70s. These transmissions could handle massive amounts of torque, and when properly maintained, could last hundreds of thousands of miles. Modern automatic transmissions, while more efficient, contain numerous electronic controls and solenoids that can fail without warning, often requiring complete replacement units costing upward of $5,000. Second, material quality. In the 1960s and 70s, manufacturers used thicker steel in body panels and frames. A prime example is the 1970 Chevrolet Chevelle. Its hood alone weighs more than some modern car doors. Today's vehicles use lighter materials to meet fuel efficiency standards. While high-strength steel and aluminum have their advantages, they're more expensive to repair and more susceptible to irreparable damage. The structural integrity of older vehicles wasn't just about thickness. The metal composition itself was different. Modern high-strength steel might be lighter, but it's often more brittle and harder to repair. When damaged, these panels frequently require complete replacement instead of traditional bodywork. This leads to higher repair costs and more vehicles being totaled for damage that would have been repairable on older models. Look at the frame rails of a 1969 Plymouth Roadrunner compared to a modern vehicle. The Roadrunner's frame could take significant impact and be straightened back to factory specifications. Modern unibody construction, while safer in crashes, often requires complete replacement of structural components after even moderate collisions. This design philosophy has turned many repairable accidents into total losses. If you're passionate about preserving automotive history and understanding what makes classic cars superior, join our community of experienced car enthusiasts by hitting subscribe. Third, repairability. The design philosophy of older vehicles centered around serviceability. Take the simple task of replacing headlight bulbs. On a 1975 Cadillac DeVille, it's a 5-minute job anyone can do. On many modern vehicles, you might need to remove the entire front bumper or wheel well liner just to access the headlight assembly. Modern manufacturers have increasingly adopted sealed unit designs. Instead of replacing a single failed component, you're forced to replace entire assemblies. This isn't just inconvenient, it's expensive. Take power window systems as an example. In classic cars, you could replace just the window motor or regulator. Modern systems come as complete units, forcing you to replace perfectly good components along with the failed parts. The electrical systems in older vehicles were also remarkably straightforward. A basic understanding of voltage and current was all you needed to troubleshoot most issues. Today's automotive electrical systems are a maze of interconnected modules, each dependent on proper communication with dozens of others. A simple electrical issue can take hours to diagnose, even with sophisticated diagnostic equipment. Even basic maintenance tasks have become needlessly complex. Changing oil in a classic car meant removing one bolt and waiting. Modern vehicles often require special procedures to reset maintenance computers, specific oil weights that cost 3 times as much, and complex filter housing designs that make simple oil changes a potential source of expensive repairs. The true cost of modern vehicle complexity becomes apparent when we examine specific repair costs. A failed mass airflow sensor in a classic car wasn't possible because they didn't exist. Today, this single sensor replacement can cost upwards of $400. The oxygen sensors that monitor exhaust gases? You might need to replace 4 of them at $200 each, and many vehicles require specialized diagnostic equipment just to calibrate them after replacement. The complexity issue extends throughout modern engine design. Consider timing chains, a critical engine component. In classic V8 engines, replacing a timing chain was a straightforward repair that could be completed in an afternoon. Modern engines often require removal of the entire front of the engine, with repair costs frequently exceeding $2,500. These complex timing systems now incorporate variable valve timing, requiring additional solenoids, sensors, and control modules, each one a potential point of failure. The data from automotive repair shops reveals a startling trend about modern vehicle failures. Statistical analysis from major repair facilities shows that electronic component failures account for 80% of modern vehicle repairs. In contrast, mechanical failures were the primary concern for classic cars. The key difference? Mechanical issues typically provided warning signs and could be prevented through regular maintenance. Electronic failures often occur suddenly and without warning. Take the modern start-stop system designed to save fuel at traffic lights. This system requires a specially designed starter motor, enhanced battery, sophisticated control module, and reinforced engine bearing. When any part of this system fails, the entire car might refuse to start. The cost to replace these components often exceeds $1,000. Classic cars used a simple starter motor that could be replaced for under $100, and their engines were designed to handle traditional starting stress without additional reinforcement. Modern fuel systems have become particularly problematic. High-pressure direct injection systems operate at pressures exceeding 2,000 psi compared to the 40 to 60 psi of classic fuel injection systems. These extreme pressures require precision components that can't tolerate even minimal contamination. A single tank of poor quality fuel can lead to injector failure, requiring replacement of the entire fuel system at costs exceeding $3,000. The dashboard of a modern vehicle contains multiple screens and digital displays. While visually impressive, these systems are prone to failure and often require replacement of entire instrument clusters. A failed gauge in a classic car could be fixed by replacing a $5 sending unit or a simple mechanical gauge. Modern instrument clusters can cost over $1,000, and many require professional programming to function properly. The manufacturing practices of the past reveal something shocking about modern vehicle production. The assembly methods themselves tell an important story. Classic cars were built with the expectation of regular maintenance and repair. Components were bolted together, allowing for easy disassembly and replacement. Modern vehicles increasingly use adhesives and welded assemblies that make repairs more difficult and expensive. Even basic components like headlight assemblies are often sealed units that must be replaced entirely when a single LED fails. Consider the interior trim pieces of a 1967 Pontiac GTO. Each panel was secured with screws or clips, allowing easy removal for repairs or replacement. Modern vehicles often use one-time use clips and adhesives that break during removal, requiring replacement of entire trim panels rather than simple repair. The cost of replacing a door panel has increased from around $200 in classic cars to over $1,000 in modern vehicles. The suspension systems in modern vehicles have also become needlessly complex. Classic cars use simple steel springs and shock absorbers that could be easily replaced when worn. Modern vehicles often employ electronic adaptive suspension systems with multiple sensors and control modules. A single failed sensor can trigger the entire system to malfunction, leading to costly diagnostic procedures and repairs exceeding $2,000. Even paint and bodywork has become more complex. Classic car finishes could be color-matched and blended using basic techniques. Modern vehicles use complex multi-stage paint systems that require expensive equipment and specialized training to match properly. A simple fender repair that might have cost $500 on a classic car can easily exceed $2,000 on a modern vehicle. The use of aluminum and composite materials in modern vehicles has further complicated repairs, requiring specialized tools and techniques. The braking systems tell a similar story. Classic cars use simple hydraulic systems that could be maintained with basic tools. Modern vehicles incorporate complex anti-lock braking systems, stability control, and emergency braking assistance. While these features enhance safety, they've turned simple brake repairs into complex electronic troubleshooting exercises. A basic brake job that once cost $300 can now exceed $1,000 when sensors and control modules require replacement. But there's an even more concerning trend emerging in the automotive industry. Recent internal documents from major manufacturers reveal a shift in design philosophy. Engineers are now instructed to design components with specific service life targets that align with warranty periods. This means parts aren't built to last indefinitely. They're built to last just long enough. These documents show that manufacturers actively calculate the cost-benefit ratio of component longevity versus replacement revenue. This brings us to the most troubling development in modern automotive manufacturing, the integration of planned obsolescence into vehicle design. But what these manufacturers don't want you to know about their future plans could change everything about how we think about car ownership. The next generation of vehicles is already in development, and the engineering choices being made right now will determine whether we're heading toward disposable transportation or a return to vehicles built to last. The evidence suggests we're at a crucial turning point, and what happens next will impact every car owner's wallet for decades to come.